So good afternoon. Thank you. Welcome to join the electronic health record breakout session 1 and the application of the novel method in big data public health research. I'm Jaja Zhang, and I will serve as the session chair. Before we begin, I just have a few reminders. If you have any question for the speaker, you can send it at any time by pressing the Q&A button. And also you can just leave the chat message in the Zoom box. And you can also raise your hand and be invited to unmute and ask your question at the end of the talk. Depending on the presentation time, we might select 1 or 2 questions after each presentation, or we have saved all the questions at the end of the presentations. So, okay, let us get started. And so we already heard at this morning's session with the increasing use of the big data in the healthcare. And so this is a very challenging time of how to utilize the big data health to answer some scientific questions in public health. So in this section, we actually switch our gear to how to analyze this data set. We have 4 speakers, each will have 25 minutes to share with us about their work with the variety big data analysis technique, including the machine learning, causal inference, and network analysis, and their application in public health research. Now, let us welcome our first speaker, Dr. Peng, a Chief Health Information Officer for the Duke Medicine. Dr. Peng is responsible for the vision and the strategic planning of the clinical and analytic information systems that impact patient care, research, and education, and had research interest on using health information technology to improve the quality of care and the patient safety in both the ambulatory and the hospital settings. He will talk about the ABC of predictive model governance. So thank you for Dr. Peng.
Okay, so to do a sound check, can people hear me?
Yes.
Great, yes. Well, thank you so much for taking time on a Friday afternoon to hear about our experience at Duke at figuring out how we oversee the portfolio of predictive models that are being used at the bedside to help our clinicians and operational leaders make the best decisions on behalf of our patients. So as Jaja said, I have the privilege of serving as the Chief Health Information Officer. And in that role, I get lots of, over the last few years, lots of people have been knocking on my door. And in many of those people, I have had a lot of interest in developing predictive models, and they want to get data from the electronic health record, and we help them, and that will be a separate talk. But many of them have gone as far as building many predictive models, and they say, hey, these predictive models may show some really important insights, and we want to implement them and put them into the hands of clinicians or folks who are in healthcare. And I would say that in our journey in the last couple of years, we have learned a lot. At times, it seems like a lot of fun to be to help all the different constituents to get models into the hands of clinicians to better influence care. But at other times, it can feel like Wild Wild West when everybody who wants to implement the model may not have thought through the implications. And from my perspective, both as a leader and as a clinician, I want to know whether these models, are they going to work? Are they going to be reliable? And more importantly, will our clinicians trust them? And at the end of the day, will they actually make a positive impact on our patients? And it is at times a challenge to work through some of these issues. I think all of you, myself included, who have developed models, it's no easy task. It's like birthing a baby, and all of us want our models to have an impact. And sometimes it's hard to have the conversations to basically talk through whether the baby is pretty enough to be presented to the rest of the world. And of course, we are not the only people who build predictive models. There are vendors out there in industry that are busy doing that, and they're interested in selling those models to us. And a lot of folks may have very pretty AUC curves to show us, and they may even have a compelling argument, but those questions still remain. Will those models work? Will our clinicians pay attention to them, and will they make a difference? So in many ways, the world of predictive model has, for us at Duke, been a bit of a wild, wild west until more recently. But it is at the same time that the Food and Drug Administration has started to pay attention to how predictive models are used at the bedside. And they are trying to govern the commercial use of predictive models in healthcare. So in many ways, we are trying to figure out how do we leverage this really exciting movement in big data for healthcare and do it in a responsible way. And of course, these concerns are not just theoretical. I've included on this slide a few examples where predictive models have fallen short of people's expectations. And that predictive models sometimes can perform well at one institution, but may not do well when you just lift it up and deploy it as is in another. That's what they found in the University of Michigan regarding some models that Epic developed. And then in other cases, models may have different forms of bias inherent in the model or inherent in the way that they are implemented. And of course, the federal government has expressed a lot of interest in this through the 21st Century Cures Act, which was put in place to foster innovation. Part of the legislation really wanted to lay out some ground rules regarding what types of decision support tools would be considered a medical device and would be subject to the regulation of the FDA as a medical device and which ones are not. And I have here on the slide summarized at a very high level some of the guidance that have been published from the Food and Drug Administration. The 4 criteria I've listed on the left talk about the criteria that need to be all met in order for a piece of decision support not to be considered a medical device. I'll let you guys read them. But if you take a step back, the spirit of the draft guidance is heavily weighted on the intent of the decision support tool. It really wants to understand whether the recommendations on these tools are going to be looked at by clinicians critically, or whether they are going to be just carried out blindly. They call this concept an independent review. Can the clinician independently arrive at a conclusion based on the information that was put into the model? That were the inputs of the model. The guidance also looks at the scenario in which the models are supposed to be deployed, and all of it hinges on how the recommendations influence the decision-making at the point of workflow for the clinician. So to focus on Duke, this is where things looked like about 2 years ago, maybe 3 years ago, before the pandemic. We started on this journey of implementing different types of predictive models. They were really exciting. They came from different places. Some came from vendors, some were internally developed, some were deployed out of the box, some were customized. On a good day, I can tell people very quickly, these are the models that we have deployed and how they were being used. That was the little house of predictive model that we lived in. But fast forward 3 years later, we have over 50 models that are being used at different places within our health system, influencing decisions in different ways. So if I was a real estate agent, we can say that our house is expanded and it looks like this. But I will be honest, as a healthcare leader, with models that are being deployed at different places, and who knows whether it's actually making a good difference and whether they're even working, it feels a little bit like this, with rooms kind of being built on top of one another, models that might be suggesting 3 different things potentially to the same clinician. And this was in some ways a brewing situation that we needed to take care of in our complex healthcare system that is Duke. And of course, as I've already alluded to, these models can come from different places. I've listed them on the right-hand side of the slide. But it's not just about where the model comes from. The teams that develop the models, whether they're internal teams at Duke or teams at other academic medical centers or even vendors, they have different skills, they have different perspectives. Some may be solely trained in data science and biostatistics and may not know a lot about clinical workflow. Others may not be fully aware of the tips and tricks we have learned the hard way to figure out what are the ways that work and what ways that don't in informing clinical decision making. And of course, a lot of these teams have different levels of expertise and resources. One common issue that we run into is that that a lot of these teams are very excited to build the models, but once they've built the model and published, they want to walk away and move on to the next project. So getting these models into the hands of a healthcare system that we can rely on 24/7 can be a challenge. And as we thought more deeply about this issue, and then I talked about this somewhat last time I was at this conference 2 years ago, if you think about this, predictive models could have unintended and negative consequences. Predictive models could potentially lead to recommendations that don't really mean much. They may not actually lead to direct actions, and we've learned the hard way those recommendations end up frustrating the clinician if you just tell that the patient is about to die, but you don't offer up what is wrong and what can be done about the situation. It doesn't help. Worse, some of these recommendations could be plain wrong or misleading. And then we have to think about the human side of things. Clinicians are busy and have different levels of knowledge about biostatistics. AUC is not a commonly known acronym in the clinical world. So clinicians can downright reject these prompts or recommendations, or worse, they might just finally follow them because the computer told them that they should do A, B, and Z. And then, as I alluded to before, we have little knowledge oftentimes of whether the models are leading to better outcomes, let alone better decision making. And then I've highlighted some of the risks related to the FDA looking at this issue. There are folks at our institution who worry about whether we might inadvertently put in a medical device that have not been looked at carefully, not been approved, and what if the federal government came knocking on our door? And then making sure these models just work. Whether it's 4 a.m. on a Monday morning, or whether the model actually continues to perform the same way 6 months or even 6 years after they were first put in. So these were some of the challenges that we recognized we needed to attack. And I will tell you that in talking to many of our colleagues around the country, this is not a problem that's been solved. And I think we think that we have actually made a lot of headway in addressing this challenge. And one of the things that was happening as these challenges were bubbling up is that Duke was organizing its big data and data science efforts around this umbrella called Duke AI Health. And this is the website that you will see when you Google us. And the tagline for Duke AI Health, interestingly, is about ethical and equitable data science. There are lots of organizations that are focusing on developing prediction models, and we do a lot of that as well. But our focus, interestingly, has been on making sure that we deploy effective, ethical, and equitable models. And the way we're going to do this is to make sure that not only do we develop models, but we evaluate them and really pay attention to the details of implementation. Because after all, we're not just talking about Amazon making recommendations of what shoes to buy, but really about what decisions are going to be made on behalf of patients who may be very sick and vulnerable. So in that context, we actually formed an oversight committee called the Algorithm-Based Clinical Decision Support. Bit of a mouthful, but the acronym is ABCDS, which rolls off the tongue. So that long name has stuck. And this oversight committee is a framework for oversight and evaluation of clinical algorithms created for use at Duke Health. It doesn't matter where it comes from. We want to put it through the same process. And it is really meant to foster innovation, to help people think about the right things up front, to make sure that we have safe, equitable, and high quality patient care. And I'll talk about how we do this throughout the life cycle of the development of these predictive models. And immediately after we formed the committee, one of the things that we came across is, well, there are prediction models of all stripes. There are models out there that have been they're actually even recommended by professional societies. They are in some ways calculators that are available not only widely, but are recommended for use, such as the Wells score for the evaluation of pulmonary embolism. And those are what we call standard of care prediction models. They're certainly data-driven. There's a lot of good science behind it. But those tend to be the lower risk ones that we have been implemented in our electronic health record for years. But then there are models that might have been developed with amongst clinicians, just getting into a room talking about what they should do. But oftentimes more common is that they are forming they take an existing rule and they want to or decision rule or calculator and want to apply it in a slightly different way or in combination, because there is no solid evidence of better way of using or making decisions within that particular clinical context. We call those local clinical consensus models. And then there are models that are in many ways developed out of maybe a couple organizations, maybe just out of one organization such as Duke, or maybe one vendor. And the recommendations certainly are not, no use of these models are not standard of care. And those are the ones that we have focused a lot of our energies on, because those are the ones that are most subject to some of the risks I outlined earlier. And the way we have set up this framework actually models after how the FDA look at medical devices. We have divided up the life cycle of predictive models into 4 different phases. First, you develop a model. And once a model has been developed and you have retrospective data that shows that it could work or it could actually make things better in healthcare, we ask for the models to undergo what we call a silent evaluation period, when the models actually put in place in the computer. It will collect data prospectively, but the recommendation is not going to be shown to any clinicians. So that's the silent evaluation. And at the end of the silent evaluation period, we want to really understand how the model is going to perform and how it's actually going to influence decision making. So we ask for the actual user interface design to be reviewed with us. And then once the silent evaluation has been completed and there's still enough promise, we ask for the model to undergo some form of effectiveness evaluation to show that it actually will not just generate pretty AUC curves, but actually will make a difference in patient care or operational efficiency. And in this, after the evaluation is done on clinical effectiveness, we allow the model to go into general deployment. And what we have done is that we have set up these checkpoints labeled G0, G1, G2, and GM at the transition of each of these phases, so that we actually help the model owners make sure that they have everything ready to go into the next phase and to also think ahead. The GM refers to ongoing monitoring, so that so we ask the model owners to start thinking about a monitoring plan early on, and definitely at the time when they're ready to go into general deployment, so that there is not just a plan, but resources ready to execute on the monitoring plan. And then in terms of practicality, because we are catching a lot of models in different phases in this life cycle, we get them registered, which is a very simple form that they fill out, and then we put them into one of these particular potential checkpoints. So we have different models at different phases of our life cycle at this point. And the committee is formed of different skill sets. I have the privilege of co-chairing the committee with my colleague, Dr. Consina, the Vice Dean for Data Science. And we have a program leader assigned to this committee. We have skill set from the regulatory and legal area, helping us interpret some of the guidance from the FDA. We have biostatisticians and clinical researchers who inform us in terms of the evaluation methods and approaches that would be appropriate for operational modeling. And then we have another group of applied data scientists and clinical leaders who help us think about the implementation issues and monitoring. And together we really form a motley crew, which we call the ABCDS committee. And if I could plug this committee for a second, we are actually hiring to help us scale up this committee. So those of you who are interested in being part of this, you can actually go to the job search website page at this conference and see the job posting there. We're hiring a leader to help us scale up the project and make sure that we have a robust evaluation and monitoring infrastructure. And we've done a lot. We've only been in existence officially for just over a year. We've done a lot in refining our processes and make sure that we are efficient and effective and responsive. We have a website to make our criteria for each step of these checkpoints very transparent and clear. And this is what our portfolio looks like today. Depending on how you count, we have over 50 models now, and some of them have been retired. And this is where our metrics were as of a few months ago. And we have a robust pipeline of models that are undergoing development. And when they're ready, they can come for the first checkpoint, and we will help them think through some of those implementation issues and evaluation issues. Of course, this is not without its challenges. As you can imagine, models come from different places and can be deployed in a wide variety of channels. If the models are targeted towards administrative or operational staff, you might want to show them in applications that operational leaders or staff use every single day. In contrast, if you want to influence decision-making, you might want to show the models within the electronic health record. And trying to figure out how these different mechanisms or models can be monitored over time is actually one of the active challenges that we're working on. And we're in the process of looking at platforms that will help us do this because we recognize that with 50 plus models, we cannot do this manually in any effective way anymore. And some of the things that we will definitely focus on looking into the future is to deploy these predictive models in what's called in the IT world DevOps. Of course, there's a new term called machine learning ops model. Basically, it allows you to build models with the purpose of with the eye towards deploying it and monitoring it over time. This is a concept that is actually very well used in software development now. We certainly want to focus on health equity, and we're actually in the middle of coming up with some guidelines to make sure not only are models effective, but they are equitable across different gender groups or racial groups. Lots of predictive models we know are coming from the imaging world and digital pathology world around diagnosis. So we are going to be establishing guidelines for how to look at those models. And we have some aspirations for making what we do here repeatable and shareable with other organizations. So that's all I have. It's certainly been an exciting journey, and we look for, certainly we haven't figured everything out, but I think we've done quite a few things to make sure that we are closer to supporting ethical and equitable data science at Duke. And so I look forward to further dialogue with this group around what we have done and what you have done in your organizations along those lines. So thank you very much. And of course, I want to thank my colleagues who've really done the lion's share of the work in moving us forward.
Thank you very much for the excellent talk. And so we do have 1 minute left, and we could take one quick question. And actually, we got a question from the Dr. Sheldon that asked about key stakeholders, providers, and patients involved in the model development.
Yeah. So, Laurie, this is a great question. Thank you for asking. Yes, they are. And I will say that models are developed without the intended consumers in mind are doomed to fail. Let me make this bold statement. It's not evidence-based, but it's certainly based on experience. So you want to understand when you develop the model, how it could be used, how it could change decision-making, what would be the state of mind of the person you're trying to influence, what dilemma or what decision they are trying to address in order for the model to actually provide meaningful and helpful recommendations. And that is the #1 pitfall that I see repeatedly, at least at Duke, amongst the data scientists.
Great, thank you.
Okay, thank you. Yeah, and so let us turn to the second speaker. And if you have any other question to Dr. Peng, and just put in the chat box, we will discuss that at the end of the talk. So our second speaker is Dr. Lee from the UT Health School of Biomedical Informatics and the Center for Biomedical Sentiment and Data Intelligence, and where Dr. Lee received 3 years of postdoc training and worked as a research scientist for 1 year. Dr. Lee actually has a unique interdisciplinary background in both informatics, science, and medicine. She will talk about how to use the AI and the EHR for the disease risk prediction. So thank you. Yeah.
Thank you. Your just introduction, Dr. Jaja. Let me share my screen first. So you can see well, right?
Yes.
Okay, thank you. Yeah, today I'm happy to present our study on behalf of Dr. Tao. Our topic is using AI and EHR for disease risk prediction, taking dynamic prediction of bleeding and ischemic risk after coronary stenting as an example. So artificial intelligence is like a superstar topic. As human being, the intelligence is so important for us as the Homo sapiens. For thousands of years, we have tried to understand how our brain, just a mere handful of matter, can perceive and predict and manipulate a world far larger and more complicated than itself. So artificial intelligence is concerned not just the understanding, but also building intelligent entities. Right now, the impact of AI will be more than anything in the history of mankind. This is predicted by AI expert Dr. Kai-Fu Lee. So like in the healthcare field, the AI algorithm now equal or exceed expert doctors at diagnosis many conditions and have very extensive applications. So for the electronic health records, since the big push in 2009, just initiated by the Obama administration, until 2017, majority of hospital and physician office have access to the EHR, and it's an established feature of the U.S. healthcare system. So the value is very significant for the EHR. So they can just facilitate better clinical decision making, improve efficiency, and lower health cost and better health care. So as from my personal experience, I think the EHRs open a new and broad world for biomedical researchers and data scientists to explore and serve as our indispensable resources, almost like the crude oil. So in the following, I'd like to share with you our own journey in the exploration of EHR using AI. So the specific title is that AI-aided dynamic prediction of bleeding and ischemic risk after coronary artery stenting and subsequent death. This is funded by the HA. So first, I'd like to show the majority of our group. This is led by Dr. Tao and comprised of multidisciplinary experts, including the clinical cardiologist, data scientist, computer scientist, and statistical expert. So the introduction, the coronary artery disease is a leading cause of morbidity and mortality in both United and globally. So the PCI, particularly drug-eluting stent implantation, is among the most frequently performed revascularization procedure in the treatment of CAD, also the very effective. However, the PCI though reduce the risk stenosis, but the ischemic risk still remains. So as a very cornerstone therapy, the dual antiplatelet therapy comprising aspirin and one P2Y2 inhibitor, they can reduce the ischemic event. However, the management just pose a dilemma, so in which if too long, prolonged duration could lead to bleeding, but too short will increase the recurrent ischemia. So how to achieve the personalized decision making as published in Circulation. One researcher said a personalized approach consider each patient's relative and absolute risk of adverse event should be considered when just decide the intensity and duration of that. So the wider used predicted scores is the one is the representative one is the depth score. So the depth score, they use 11 features to then just the very easy dashboard, then very straightforward to get the benefits and the risk of continue or not continue debt. But it also has obvious limitation. The first one is the static and fixed prediction window that's hard to support flexible and fine granularity risk estimation. The second is the classic Cox regression. It's a little bit hard to learn from high dimensional data, especially the big data. So our objective is to leverage AI models to dynamically predict the adverse endpoints. So for the method part, just from the study design, just namely the dynamic prediction scenario and data source study cohort outcome and characteristic definition and AI modeling. So this is our whole framework of the research. So for our benchmark baseline, we choose the depth score as a comparison. So for the, we can see that the prediction scenario is quite static. It only just predict, this is the after the first stent implantation. So they predict 12 to 30 months among just during this interval. So what's the ischemic and bleeding risk if the patient continue or discontinue that? By contrast, we design a very dynamic prediction scenario, means that we have like the total interval is the same, but we have more smaller granularity, like 3 months, 6 months, 12 months, and 18 months as the interval. And our input also dynamic, means as the prediction start time varies, the input can just get increased as more available data, more data are available. So the data source is about user Cerner. This is a real world identified data set, and just a really large patient numbers. And the original cohort means the patient who received the drug-eluting stent implantation, so about 158,000. So after a series of exclusion include like a patient with lack the important patient have incomplete records or not without age information or less than 18 or like too short follow-up records. So we just get 81,000. Then we just random split into the training, validation, and test set for AI model development. This figure demonstrate our like 3-layer just the data processing pipeline, means we just try to get comprehensive multidimensional information for the model input. So this is the definition of the intervention, means the depth regime, and the outcomes means the what we would like to predict. So this is depth. This is the ischemic, means the composite of just the ischemic heart disease. Also include the cerebral vascular, means the stroke, and the bleeding means the composite of bleeding disease and also the blood transfusion. So for the this is the baseline characteristic, including the demographic, cardiovascular history, and the important comorbidities, as well as the co-medication. And so we just choose 5 type of AI models. 3 are the just the traditional machine learning. The light GBM is relatively new. This is a highly efficient gradient boosting decision tree with the strength of faster training speed and good accuracy. And the logistic regression and random forest is very classic. And another 2 deep learning is the RM-based. One is the bidirectional GRU. The strength is can catch both too short or long-term memory using gate mechanism. Return, this is like aim to improve the clinical prediction model interpretability. So this RM-based has the strength to deal with the longitudinal EHR data. And this is the basic just the structure of the model. And so for to increase the model interpretability and better to let our stakeholder to understand and the prediction result, we just use the shape to visualize our the important clinical features as well as the risk scores. In addition, we make the input more dense. We just apply a hybrid strategy for the code conversion, including the first, if they are the labeled characteristic, we just use this as the input as the tag. If not, we use like a category level CCS code. If not included here, we just use the original standard code like CPT, ICD, or like HCPS, then just to enhance the visualization. So for the result, baseline characteristic. So for the important, we just compile with the event. We have two types of endpoint. One is ischemic, another is bleeding. And so for the ischemic event, so majority is without event. The same is the bleeding. And for the baseline characteristics, so interesting that no matter the bleeding or ischemic, most of the event group, they have higher prevalence of the cardiovascular or hematology disease, also higher rates of risk factors and comorbidities and co-medications. So for the prediction performance, because we compare the DAPT score as the baseline, so in this, they only provide this 12 to 13 months window. So this is our most important comparison and just the scenario. So we can see that the blue is the LGBM and the red is DAPT. So in both ischemic and bleeding, our just the LGBM outperform the DAPT. And for other scenarios, because we have designed a total 8 scenarios, so only this one, the DAPT covered, but for other scenario, the DAPT score not covered, our models there perform just a stable and robust performance. This is for the ischemic, and this is for the bleeding. So for the visualization, we just this is our this is work is the ongoing. We will just design a dashboard to demonstrate our prediction result, including the specific probability score as the time progress, as well as at the specific time window. What's the particular or specific just highly contributing features that will influence the at the end point occur, means that, for example, the bleeding risk. So the most important, like the DAPT. So if the patient take DAPT, then the red means the 1 means that this red represent 1, blue represent 0. Means if patient take DAPT, then the shape value is in this side, the negative, positive side means take DAPT will increase the risk of bleeding. And let me check my time. Okay, that's fine. So yeah, sorry. Okay. Yeah, and yeah. So other important features like the bleeding history and anemia, and also the prior blood transfusion or CKD. So, and also cancer. So the cancer seems not just revealed as a risk factor in the previous studies, but from our study, we discovered cancer is also a very important feature to influence the occurrence of adverse event. And so for our limitation, the main limitation is the data. So it's the incomplete nature of the EHR data. For example, the DAPT record is the vital information for us, but it's very just evident missingness in the Cerner data. So we have to, because we needed to stratify the patient as the continue or discontinue group to train the model. So currently we just use just hypothesize or define the time threshold to stratify the patient into continue or discontinue group. So if the just the status was based on an inappropriate assumption, it may just generate a researchers created bias. And another is that certain information is not available, like the stand like a diameter, length, bifurcation, or what's the cause of death. Maybe this is restricted by the structured EHR. If the clinical notes maybe can as the complementary information source. So also because we just use the standardized medical terminologies, so we cannot control the possibility of coding variability. For example, the very important endpoint like standard thrombosis not covered in the ICD code. So we just use alternative ways to file them. So it's not also just pose some possible errors. And for conclusion, so the development of dynamic clinical prediction model represent an important methodology advance in the field of precision cardiovascular medicine. So as the first effort dedicated to dynamically forecasting adverse endpoints after PCI, our AI-empowered approach demonstrates promising capabilities for risk factors. So this approach holding value as a novel clinical tool that can refine the prognostic judgments of the clinicians and facilitate achieve the optimal data management. So my just insights or what we try to just make efforts is if we want to further increase the predictive performance and the clinical significance of our AI and EHR-based research, I think we could try to improve in three perspective. The first is data-driven, means we just do better definition and processing at the very beginning of our research, like design, just carefully select what's the important variables, what's the the cohort, and what's the limitation of the data, just to make a very careful research design in the first step. And we can also seek a better quality data set. Maybe just enlarge the dimension to the clinical nodes or imaging, to from multi-dimensional complementary data source. Then the second part is the data model driven, means as the AI model and just continue evolving, we have more and more weapons to utilize to for our research. For this research, we will plan to use like a transformer based or the deep learning based survival model, to further to make the performance more robust, and also just increase the interpretability and explainability for the model, and try to make the model more reliable and easy to be accepted in the clinical practice. And the last is the knowledge driven. Means because as the data scientist, we needed to keep very frequent communication, discussion with clinicians. Then they can guide and just make our research make sense. And further, we just engage the patients and the stakeholders, and to just know what they really want, and what we do is really makes sense. So as Jeff Dean conclude his TED talk in the concluded his TED talk, he just said we are truly in an exciting time. So I think this is applicable to our research. So even we face the imperfect electronic health records data, and also the AI model, a lot of maybe complicated mechanism needed to master, but I still have very confidence and passion to just do the research that really makes sense in the clinical practice. So finally, I'd like to acknowledge the support from the AHA and also the precision medicine platform from the Amazon cloud. And the most important one, I think, should be our multidisciplinary teamwork and very collaborative work led by Dr. Tao. So yeah, if you have any question, could ask me or Dr. Tao. And also, if anyone want to join the EHR and the related research, welcome contact Dr. Tao to join our group as PhD student, postdoc, or like a faculty member. Thank you so much. I'm not sure what's my time right now.
Thank you. You're well on time, no problem. And so we do have time to accept 1 or 2 questions. So if you can see, we have the question on the chat box. And the first question is from the Dr. Davis. And he's asking you about the methods, the machine learning models you use are proprietary or open sources.
Oh, yeah. So yeah, open source. That's actually yeah, this all just this public available about the paper and code. Yeah.
Okay, so the second question from the Dr. Davis is about how you are making sure that you stay engaged with the clinician.
Oh, yeah. Actually, our team member have 2 cardiologists. Yeah, they just focus on he focus on the PCI procedure. Yeah, he's a relatively general like practice in cardiology field. Yeah.
And so the following question from Dr. Davis is that from your experience, what would you recommend for the data scientist without healthcare background to make connection?
Oh, let me, so would you repeat again? Repeat the question?
From your experience, what would you recommend for the data scientist without healthcare background to make connection?
Oh, yeah, I think this could make effort from several ways. The first, it's better to have a good like a leader, team leader, like Dr. Tao. She has extensive like resources, expert resources, right? Extensive collaboration. First, can contact the relevant and very important expert. The second is, as a data scientist, if we don't have the background, I think first just besides discussion with them, and also needed to use time to read the papers and just try to understand the medical problem, and also read the paper like the current guideline and the related research, and try to understand the details. Then just to make sure you really get the point of the data, and also how to extract the outcome and the important features and design the study. I think for sure that means that first you just find the right expert, and that's the external, and for the internal, just make effort to read the paper, read the guideline, know the knowledge about the topic. Yeah. Yeah.
So the last question, and we will start the next presentation. The last question we have is for I think it's from Jordan, for the Shapley approach. Assume the feature contribution are additive. Do you think this is a reasonable assumption for this problem?
Okay, let me try to understand this question. Yeah, actually, yeah, the Shapley, they just they actually they don't understand the features, right? But they just the Shapley just try to plot what's the important variables for the model. Means, oh, okay, for the algorithm, right? For this LGBM. So for the model itself, what's the important input for the model? They just output this like a little bit like the just the parameter weight, and this is just from the model itself to generate what's the important like input or variables that influence the prediction result. Yeah, this this is still a little bit a step from the interpretability. This means from the model itself, oh, what's this feature influence the prediction result?
Can I follow up with that? I asked the question, sorry.
Okay.
Do I have time to follow up? Is it okay?
Yeah, that is okay. Just a follow up.
Yeah. So no, I understand that the Shapley doesn't, it's not going into the model predictions itself. But as far as the interpretation goes, the game theoretic approach behind the Shapley value, the game theoretic assumption is basically assuming that you can break down the contributions of the features one by one, so it's in an additive way. So it's not really capturing interactions between features, whereas the model that you're using has lots of interactions in it, right? So I'm just kind of wondering whether or not Shapley is really giving a good indication of feature importance here.
Okay, yeah, the interaction, yeah, actually the Shapley, it can also plot like the interaction feature figure, not this type. This is like this is the bee swarm, means the important feature, but for the feature interaction, it plot in another type of figure. Yeah, that's the interaction. Yeah, so yeah.
Okay, thank you.
Yeah, thank you.
Okay, thank you. Thank you for the excellent talk. And let us welcome our third speaker. Our third speaker is Dr. Jamshidi from the Computer Science at the University of South Carolina. Dr. Jamshidi directed the AI System Lab at the University of South Carolina, where he developed the theory in causal AI and statistical machine learning and applied the theory to solve problems in computer system, robotic learning, software engineering, and public health. He will talk about the reliable and transverse clinical diagnosis and decision-making with the causal AI. Thank you.
I'm sorry, I needed to unmute myself. Hi, everybody. Thanks for coming and joining to this session. I would like to talk about two things in particular in this talk. First, a little bit of background of causal AI and the collaboration that my group have with several other colleagues at USC, in particular, few colleagues in the Department of Pharmacy in the context of cancer, colorectal cancer in particular. So I give you some few examples. I don't go into much detail about those, but also in the second part, I will talk about some a particular example to give you an idea for some of you who are not familiar with this causal AI, what are the benefit or potential benefit in healthcare and in general in science. So that's the plan for today. Okay, so for the effort that I mentioned, I'm sorry about this busy slide. Don't worry about that. So it's basically a snapshot of the workflow that we think, at least for this project that we have with my colleagues. Let me explain some detail about this. So imagine that we have, in this case, some research about identifying different factors that potentially influence and might be influential for like the cause of colorectal cancer in this particular project, but in general you could think about it the cause of any cancer or cause of any kind of diagnosis in healthcare. So these are like interesting questions and have potential impact in the type of research that we do and for the life of many patients. So if you look at the left side of this figure, you see that we have obviously some experimental data, whether this experimental data could be, for example, the kind of measurements that we do in the lab, either human patients or mouse or other subjects. So we collect data, and by default, we know that there are several statistical analyses that have been done since many years ago. These are traditional standard analysis, nothing new here. And also more recently, we know that due to popularity of AI, in particular deep learning, many effort has been done in doing many interesting tasks. You have heard about protein folding and a lot of these interesting, fascinating research that has been enabled by deep learning. So these are also become kind of a standard process in healthcare. And obviously, you know, these issues of deep learning models or in general, any ML models being black box, and we would like to provide some explanation to provide why such prediction came out of such models. So these are, you can think about it as a standard approaches, but if you look at on the right-hand side, basically causal AI is a methodology, you can think about it, that provides some insight that we can even reason about causality, whether this is cause of a disease or something else, from maybe observational data. The most ideal scenario for identifying or claiming or recovering any causal relationships is the best way is to do experiment. And I will give you a particular example later on that in some scenario it might not be possible, some scenario might not be ethical, and in some scenario it could be very costly. But observational data have been collected in any area since many years ago, and still it's possible to do it in lab. And we would like to infer causality from these observational data. And causal AI is a direction and provides some foundation, including some calculus to recover or infer causality from observational data. And in particular, this is an example in this direction. Instead of building a model that its interpretation would be difficult, we would like to build a much simpler model that even scientists could interpret and could build something, could make decision that has more evidence and would not be confused, would not basically make a decision because two things might be correlated in the data point that they have collected. Also, as a part of this research, we do build infrastructure to facilitate, because we know that this data collection, processing that infer some sort of a model that we call causal model requires a process, and for this process we need infrastructure. And I'm not basically a healthcare researcher. My expertise is in core theoretical machine learning, also systems, computer systems. So we collaborate with scientists in order to build such systems. But let me start with a particular example. And this example came out of this paper that I enjoyed reading a lot, so that might be useful. And please do stop me and ask your question if you need any clarification. And this example is fictional. But imagine that we have a patient waiting for a heart transplant, and on January 1st, he received a new heart, and unfortunately, 5 days later, he died. Now imagine that we can somehow know that this person Zeus not received the heart transplant on January 1st, then he would have been alive 5 days later. So this second scenario is called counterfactual in causality terms. And you already know that in this scenario, it's not possible to see the outcome of counterfactual. And to clarify, in this case, heart transplant is the intervention that we did in this process. These are the standard terminology in causal AI and in some other contexts too. And imagine that all other things and the life of this patient has been unchanged in this counterfactual scenario. Now, let's imagine whether we can reason what would have been the cause of Zeus deaths. And in this scenario, you can easily see that the outcome of the actual scenario, the actual world, and the counterfactual world, since they are different, we can easily infer that the transplant caused Zeus death in this scenario. But you already know that we never know this counterfactual world, what would have been the outcome of that. Now imagine another scenario where another person, Hera in this case, received a heart transplant. Same day and 5 days later, she was alive. And again, imagine that somehow we know that if she had not received the heart transplant, she would have still been alive 5 days later. If you think about this scenario, and imagine that all other factors have been unchanged, you know that the transplant didn't have any causal effect in this scenario. And the reason is that the outcome of both the actual scenario and the counterfactual world is the same, remain the same. Now imagine that we have collected data. Here you see that Zeus person, both outcome, and also in this case, on the right-hand side, you also see the outcome of the actual world and the counterfactual world, and also for Hera the same way. So on the right-hand side, you see that for Zeus, the outcome is different, and for Hera's, by the way, one shows that this person actually died in this scenario. So again, if you think about it, we cannot have this situation. We cannot have this situation that we know what would be the outcome in both scenario in any, at least within this example, where the lives of persons are involved when an intervention has happened. So ideally, so in reality, we would face this situation that either if we did any intervention or not, we only have the outcome of that scenario. And the counterfactual world, you see question mark, meaning that we don't know. So in this situation, the question is that what we can do about it, whether we can infer any causal effect. And if you think about it at the individual level, for each person, we have no way to infer any causality or any claim about causality of any intervention. But the good news is that at the population level, there is some reasoning, there are some foundation that we can maybe reason about the causal effect of this intervention in this particular heart transplant. So in this case, you see that basically for Zeus, we see the basically the question mark, and also the same way for Hera. Okay. So what is the population causal effect? Population causal effect, again, is a way to estimate, and this estimation could be inaccurate, similar the way as other statistical analysis, but give us a way, a mechanism to reason about causality and have some estimation about the causal effect of any intervention. And again, to repeat that, to contextualize that in any healthcare scenario, in any even beyond healthcare, in science, as a researcher, if you do some research, typically it involves some intervention. For example, even in computer science, where we do research, we build a system and we want to know whether this system that we built and now is deployed in production, whether it increased the revenue of the company or not. For example, if we make any change to Facebook, whether that change increased revenue of Facebook or not. So these are kind of questions that would be good to have some causal estimation for any intervention that we do to the system. So there are some definition. I don't want you to get bored, but I quickly go over them. Maybe we can discuss them later on. If you are interested, I would be happy to explain in detail, but just wanted here to explain these few concepts and some reasoning that we also have to be careful sometimes where we can claim causality and where we cannot, and at least we know that there is a correct way and there might be some incorrect way of estimating this causal effect. So here, let's define this probability of y a equal to 1 as a proportion of subjects that would have developed the outcome had all subjects in the population of interest received the exposure value A. So A if equal to 1, meaning that they have received this exposure or this intervention. And in this case, at the population level, if you look back to the table, you usually see that basically the probability of y for those who have received the intervention and died as a result is not equal to probability of basically not receiving the intervention, also died for some reasons, right? So these two probabilities, and you can easily calculate this. I can go back to this table here, and if you simply count, you simply need to count, look at this column A to check, for example, who received the intervention. For example, this one has Tia received the intervention, and the outcome is that this person did not die, right? So we should look who died and what proportion of them did receive the intervention and what proportion of them did not. And if you calculate that, simply these probabilities are not equal to each other. So in this scenario, this probability of dying is a risk, is called a risk. And in these two populations, since this probability is not equal, we cannot claim anything about the causality. And the key reason is that, here is the calculation if you look at it. And the key reason is that this probability is simply a conditional probability. And in any scenario, if you want to claim causality, you have heard about it, we need to do randomization. And this randomization actually is the key enabler in order to provide us the correctness of claiming causality or estimating the causality. You have heard about this key statement that association is not causation, and this visualization show that if you look at this visualization at the top, at the population level, since the population of those who exposed and died is not equal to those who are not exposed and died is different, we cannot do any claim because these are simply conditional distribution. And in order to claim causation, we need to have this risk equally proportioned to any two groups or multiple groups if we do any intervention. So I don't want to go into the detail of the mathematics, but the key takeaway, if you look at the math, and I'm happy to walk you through that later on, is that this basically the fact that we randomize the experiment, and by randomization, simply mean that imagine that we have a population one at a time, we flip a coin whether we want to do the transplant for this person or not, and we do that. Imagine we have like one group do the intervention, one group not doing the intervention by simply randomizing this decision. And in that case, since we did randomize, we basically cut any confounder in this scenario, whether this confounder is the age of the person, whether this confounder is the gender of the person, and so on. Since we cut these confounder effects, it provides the exchangeability between these two groups. For example, in this scenario, we put them into two groups. Could be again, we put them to multiple groups depending on the problem. But in this scenario, since intervention is 0, 1, we only have two groups. And the math is actually very simple. Basically the exchangeability of the result, because in this case, the risk, meaning that the probability of people died either as a result of intervention or those who are in the group that are not receive an intervention is equal. We can exchange this conditional probability, and as a result, we can claim that this conditional probability, this probability of y equal to 1, given whether they receive the intervention or not, is basically equal to probability of y a is equal to 1. And in this case, since we have randomization, we can actually claim that association is causation in this particular case where we have randomization. Okay. Let me finish this by saying that this is a fantastic students, postdoc in group who are doing this type of research, and I'm happy to take any question if you have. Thanks.
So thank you, Dr. Jamshidi, for the excellent talk. And is there any question from the audience? So we do have 2 minutes. If you have questions, so you can raise your hand or just unmute yourself and speak out of your question.
Hi, Puyan. It's Denise Davis.
Hi, Davis.
How are you? Okay, so from your, it's a nice day outside. From your experience so far, where do you think you can apply the causal AI and the data pipeline? Because that's what I'm looking at in your picture. At what part are you going to apply it? In the analysis of electronic medical records, or are you looking at results from tests, or you want to be able to apply it all around? That would be my question. What's your experience? Where have you found so far?
Yeah, good, very good question. So to give you a direct answer, like the most straightforward way of applying causal AI is to evaluate any hypothesis that we have that has some sort of a claim about causality. And for example, in this example that I mentioned, the claim, for example, the hypothesis is that this heart transplant, imagine that like you did some research and you develop a kind of fantastic heart transplant. Then you want to show that whether like it works, meaning that whether it has any causal effect to the like curing patient's health, right? So in this case, you need to do some experiment. But if you do the experiment incorrectly, meaning that if you do not randomize, if you test it, for example, on like, imagine a group of all women or all men, right? Since like you have these confounder as a gender, you cannot claim causality. But if you do randomize, that's a way, even if with observational data, you can infer causality. Also, you can imagine again, you have a system, imagine Google have an advertisement system and make some changes to the protocol of this system. And they want to infer whether this change had any causal effect on their revenue, for example, right? If you have heard about A/B test, that's also one way of inferring causality from any test in product. But in general, it is, you can think about it as a methodology that can help us to evaluate any hypothesis in a correct way instead of just looking at the correlation.
Well, that's exciting. Thank you. Thank you.
Thanks a lot.
Thank you very much. So we are almost the time, and let us leave any other question at the end of the session. And our last speaker will be the Dr. Wang from the Department of Epidemiology and Biostatistics at the University of South Carolina. Dr. Wang's research focused on the mathematical and statistical modeling of EGG data and MIR data and the diffusion tensor imaging data of clinical groups with brain disorder. She will talk about statistical modeling of brain disorder with topological data analysis. So thank you.
Thank you, Dr. Zhang. So hi, everyone. My name is Yuan Wang, and as Dr. Zhang introduced, I'm an assistant professor of biostatistics at the Arnold School of Public Health. So for the next 25 minutes or so, I'll talk about statistical modeling of brain disorders with topological data analysis. So as a brief overview, in this United Nations report issued in 2007, nearly 1 in 6 of the world's population suffer from a neurological disorder of some sort. So these disorders could range from Alzheimer's, Parkinson's, strokes, multiple sclerosis, and epilepsy, to migraines, brain injuries, and neuroinfections. So To improve the healthcare of brain disorders, we first need to figure out why the brain breaks down. But it's not a straightforward question or task, as the brain resembles a computing engine that requires the coherent working of different components to function properly. And what adds to the challenge is the heterogeneity of individual characteristics. So we begin tackling the problem by using reliable brain imaging tools and models. EEG is the oldest brain imaging modality and remains a staple in studies of brain disorders due to its portability and high temporal resolution. The downside is obviously the spatial resolution, as the EEG electrodes are situated quite apart compared with the size of neurons. MRI, on the other hand, provides a spatially more precise quantification of the brain, ranging from the DMRI or DTI that visualizes the white matter tracts or tractography to fMRI that captures the gray matter functional activity in either resting state or under task stimuli. EEG and MRI data are typically analyzed by signal processing and network modeling approaches. In recent years, people have begun to realize that data has shape and shape has meaning. As Gunnar Consum famously said, we need to capture the shape of the data to make better inference about the underlying brain disorders. This is where topological data analysis, or TDA for short, comes in. So TDA captures the shape of complex data with tools from the mathematical theory of algebraic topology. Using algebraic topology, topology can be characterized by wholes of different dimensions. In a topologist's eye, in this famous example on the right here, cup is the same as a donut, as they can be continuously deformed into each other while preserving the hole in the middle. A key TDA algorithm is persist homology, which tracks the evolution of topology of a data object as it goes through a thresholding process called filtration. The longer a feature survives in the filtration, the more likely it corresponds to an underlying structure rather than noise in the data. In the example on the right, the data is simulated from the shape of a circle, so the feature that corresponds to the whole of the circle lives on, while the other features die. TDA provides a framework for characterizing the shaping data, but quantifying the statistical variations in the topology is a challenge. And we need to adjust our methods, basically build our methods in different data contexts for different data types. So in the next section, I'm going to show you some statistical frameworks that I built from scratch on persist homology with promising applications in neuroimaging studies of brain disorders. Depending on the data type, these frameworks fall into two categories: topological signal processing and topological network analysis. The applications demonstrate how topological difference and indifference can be used in different contexts to highlight clinical features of interest. We'll begin by showcasing topological signal processing methods with applications in epilepsy. So in this, one of the earliest studies that I did, actually the earliest one, I proposed extracting topology from a signal by looking at the time segments corresponding to electrical potential beneath a horizontal threshold and track the changes in connectedness of these time segments as the threshold moves upward. The electrical potentials at which the time segments emerge and merge are designated the birth and death times of the time segments. And the birth and death times are coded in persistence diagram, a barcode, or a persistence landscape tracing outlines of 10 functions built on the barcode. I also wrote a MATLAB package, actually released a MATLAB toolbox or package for this purpose, for computing persistence landscapes and constructing, doing statistical inference on signals. So if you'd like, you can go ahead and download it from my research website, TDA Brain. In this application, the first application, we had a motivating data set of single trial EEG recordings at 8 channels from the patient. What that means is that we only have one segment of recording for before seizure and one segment of recording during seizure at 8 channels. And that's from, all of them are from a single patient. So the patient information that we had was that she had a lesion directly below the channel T3. So that's most reasonable, assumption, clinical ground truth that we were holding here is that that's, most likely the site where the seizures, epileptic seizures are generated. So we want to see if comparing topological features before and during seizure can provide some spatial conclusion that sheds light on seizure localization. To compare the persistence landscapes of single trial signals before and during seizure, we need to resample. But those of you who are familiar with resampling, you may be able to see that resampling in the time domain or the temporal domain here is challenging because we're not able to, by dividing up the signals, bootstrapping the signals at different, at set time points are definitely going to break up the characteristic waveforms that occur randomly throughout the 2 phases. So it hit me that we could actually solve the problem by running the permutation test that compares the features in the spectral domain instead of the temporal domain. So what we did was to permute the Fourier coefficients that we obtained from the signals that we decomposed from the signals in the observed signals. And we reconstruct the signals using the permuted Fourier coefficients for which we compute the L2 distance that measures the difference between the signals. So the process repeated at least 10,000 times until, of course, distribution converges, yields an approximate empirical distribution for the L2 distance. So comparing with the L2 distance of the persistence landscapes of the observed signals gets us the p-value. So in application to this motivating data set, we see some very interesting pattern of results. So here we see that the channels T3 and T5 show topological indifference between the 2 phases before and during seizure, which indicates that the tissue damage around the seizure region below T3 may be causing neurons in the region to fire irregularly, even before the seizure onset. The channel T4 shows a weaker indifference than T3 and T5, yet it could indicate seizure propagation, which is much added value to this application. So we have actually been trying to secure large-scale human EEG data sets to test our hypotheses here, related to the seizure localization and propagation. So please contact me if you have the resources and you would like to collaborate. Okay, so definitely a lot, to do here. As you can see here, using the, I don't know if you can see my arrows here, I'm actually pointing at the right 2 columns. The standard EEG measures are not, able to tell us, differentiate spatially the seizure region and the rest of the channels. Okay, so, but we would definitely like to test it, hypotheses with respect to, see if we can actually repeat the pattern of results in a large-scale data set instead of just a single data set, single trial data set. All right. I then developed a second test to compare persistence landscapes without a computational baggage or trial constraint. So in the first test that I've developed, it's actually quite computationally consuming. And also that method only applied to a single trial data set. So we would like to forego both of those constraints in the new method. So here the persistence landscapes may be an average over a group of persistence landscapes, which is actually the perks that come with one of the perks that come with using the persistence landscapes. So the idea here is to resample the areas under the layers of the persistence landscapes, use a Kolmogorov Smirnov test or KS test for short. Okay, so we're basically utilizing the property of the persistence landscapes in that, so we really have monotone function in the areas under the layers. Okay, so that monotonicity actually helps us in putting things in order for the KS test. So this is, I'm not sure if you're aware that you can actually compute the p-values for the KS test exactly, right? So that's, this is actually based on a combinatorial approach, and this can actually be done, fairly efficiently, without all this baggage of the standard permutation test, and you'll get the p-value. But for in the interest of time, I'll skip over the details. If you want, you can refer to my papers, which are quite detailed in describing the motivation and the process, the procedure. Okay, so the focus here is the application. So again, we applied the method to the same data set to which the first test was applied, was actually motivated by. In this, we can see that the two patterns, the pattern of results of the second test actually matches up, quite, it's actually kind of like enhanced version of the pattern of results applying the first test. I call it a standard test because it, nothing standard about it. Is basically we are using standard permutation there. So I'm calling the spectral permutation test the standard test, but this is actually the results from the spectral permutation test. Okay, so so what this shows us is that the set of results that we got, the spatial pattern of the results that we got from the first test is really not a fluke. Okay, so there is it's really showing that topology has topological inference, more precisely, has the potential for might have its place in seizure localization and also identifying seizure propagation. But again, without more extensive data confirmation, we can validation, we cannot really do much more here. So other than epilepsy, I'm also interested in stroke-related brain disorders, such as post-stroke aphasia. So I received this data set from the speech neuroscience lab at UFSC. And so online altered auditory feedback is typically used in laboratory to stimulate overt speech errors in aphasia by externally inducing mismatch between the predicted and overly detected speech. So here we studied the EEG signals simultaneously recorded under an AAF paradigm. So there are 3 pitch shift stimulus settings in the study. No pitch shift. So in this case, we would say that everything we do is with respect to the speech onset. And the second condition is stimulus setting is upward pitch shift, and then not surprisingly, downward pitch shift. So this slide here that shows you, all right, I skipped over too quickly. So actually in this data set, we actually had what's called event-related potential that are evoked with respect to the PSS pitch shift stimulus settings. And the ERP recording was actually made concurrently, simultaneously as the person speaks into the microphone. Okay, so this is all simultaneously recorded. So to see a more kind of like detailed explanation of statistical representation of the ERP, you can think of the underlying brain activity as a function here, unknown function that here we're trying to estimate, and you have some sort of statistical variation here, and then this is what you observe. So ERP is basically, a large number of trials generated with respect to that same underlying signal. Okay, so we have, you can think of the ERPs as statistical variations of an underlying pattern of activity. So here are some examples of the event-related potential, or ERP for short, response down the midline channels. So by midline channels, we mean those down, sitting right between the left hemisphere and right hemisphere of the brain. So the midline channels in all three pitch shift stimulus settings. So the ERP response at each channel is computed as the average over the trials of the EEG signals recorded at that channel under each stimulus setting. So what you can see here is that, just kind of like a quick summary. You see that the red lines here are actually for the aphasic individuals, and the blue lines here pertain to the healthy controls, or neurotypical controls. So you can see that the aphasic pattern here actually doesn't pick up this downward and upward tick of speech response, that neurophysiological response that you're supposed to observe in healthy individuals. So in application to this particular data set, actually improved. I wanted to improve the robustness of the test that I developed for the epilepsy studies. So here I actually opted for the percentiles of the areas under the PLs of two ERPs instead of using the areas directly for comparison. So this paper is already published at Journal of Neuroscience Methods. It's quite comprehensive, so you should make a nice read if you're interested in all those technical details. But yeah, again, in the interest of time, I'll skip over. So this is a pattern of the results. So the improved test on the persistence landscapes actually highlights neurodeficits at the occipital, parietal occipital, and occipital regions. So so this part, of course, we're still working on this problem. We're not stopping here. So just what we're trying to explore here, is to see what a pattern of results has to do with the sensory motor interface, which happens to be fairly close to these channels. Okay? But that's still work in progress. And one thing here to note is that you see that this pattern of spatial pattern of results here is pertains to the condition where we do not impose the pitch shift as the person speaks into the feedback loop. Okay, so when this test is actually applied to the two other stimulus settings, we actually don't have, we do not observe a distinct topological difference between the persistence landscapes of the aphasic individuals and the healthy controls at any channel. And so for kind of like to enhance the results, because this pattern here is really what we're supposed to observe across all three settings. So this indicates that we need some fine-tuning of the method, and that's when where I came up with this new method of capturing this persistent homology process on signal in different direction, rather than by imposing the threshold in an arbitrary angle, rather than just simply moving it upward horizontally, like is shown here. Okay, so now we can relax the direction in which the threshold is moving by in basically any direction that makes sense. Of course, 90 degrees is no go because we are aware that gradient doesn't exist for that line. But other than that, we are able to capture the changes in the connectedness of the arcs rather than time segments as we move the threshold in that same direction. So this gradient filtration method is able to, as expected, okay, so that's the purpose of this methodological improvement. So it's actually able to capture the difference in the persistence landscapes of the phasic group and control group in all three conditions. Okay. So that's recently we also kind of like move forward and developed a correlation method for a correlation measure for topological association between signals by correlating their persistence landscapes at different gradient filtrations. Okay. So in an application to canine epilepsy dataset, standard EEG measures do not show distinct, as you can see here, do not show distinct difference in connectivity between the interictal and pre-ictal phases. So topological correlation, on the other hand, picks up the global connectivity difference between the two phases. So the inference results, what we also noticed in our study is that the inference results obtained from topological correlation are also highly robust. What that means is that by changing the gradient range, so the range of gradients that you're allowing in the gradient filtration, it doesn't actually alter our inference results that much. Of course, you have an odd one out here, but the rest of them, it actually shows distinct difference in the topological connectivity. So we have already put this, revised this into a journal article, and hopefully it's going to be out this year. And this is another, so I've kind of like talked about focused on topological signal processing methods, which are applied at the signal level. But for neuroimaging data, those of you who already have experience working on neuroimaging data, you'll be aware that network analysis is more of the norm. So what's interesting here about stroke, the brains that have suffered stroke is that these stroke lesions actually leave empty space, dead tissues, I shouldn't say empty space, but dead tissues or holes in the brain network, right? So if you're seeing kind of like model the brain as a network, working off of different components, we actually have a lot of, heterogeneity in the holes caused by the stroke lesions. So here's written by Dr. Yoganov, who used to be a member of the facial lab at UFSC. This nice map here just shows you the statistical variation of, the stroke lesions. So the larger, this indicates the scale here, the number color here indicates the overlap of the lesion, but really you see quite a bit of statistical variation of the overlap. And that's so here really comes two questions. Is the first thing is how we quantify, how we model the holes, and the second question is how we model the statistical variation of the holes. The kind of like we have already begun answering, kind of like coming up with answers for the first and part of the second question. So what we can do here is to use the RIPS filtration to capture holes in a brain network. So here you see that this is a simulation in that ICAPS paper that's already in press, and you see this actually shows a simplified process of the RIPS filtration. Of course, you're going to have, some of these triangles are supposed to be filled in. but this kind of like shows you the gist of it. As we vary the threshold, the edges of the brain network will actually have the connectivity structure actually changes. And most importantly, this filtration is able to capture this distinct hole in the middle, okay? So this process, can take place in the brain network modeled in this way. So what we do here is that we can construct a persistence diagram that captures the process, the evolution, topological evolution in this RIPS filtration. And the problem with working with this persistence diagrams of points is that, these points do not, most likely do not match up across individuals. Okay, so we used a heat kernel to smooth out the point diagram of points, and we do transposition test on spectral components of this heat kernel decomposition. So this method here is applied to the polar data set that's collected by Center of Aphasia Recovery here, where most of my collaborators are at UFSC. So we looked at anomic people with anomic aphasia and Broca's aphasia, and at the baseline visit and after their first treatment. And we see that we actually...
Dr. Wang, it's already time.
Okay, sure, I will wrap up. Right, so so we can see that the method is actually able to capture the difference in the holes, structure of holes in the structural network, but not a functional network. Okay, so this is kind of like where the next step is. We're going to look at big neuroimaging data using topological data analysis. And a quick acknowledgement of all of my collaborators, my current collaborators, and the grants that I currently hold. So thank you very much.
Thank you for the excellent talk. I'm sorry that I interrupt you at the last minute. So, and as the diversity of the big data, actually our session try to give you a broad and overview about the diversity and the complexity of the big data analysis. So like the first speaker, Dr. Poon, provides a very big map for us for how to do the prediction and how to validate that one and how to implement in practice. And Dr. Lee gave us a review of how to using the open software of the machine learning and the AI to predict the bleeding and the ischemia, and including the visualization and the interpretation. And we go actually very detailed and next for the experts from the computer science and the biostatistics give us a very deep and totally new view of the big data analysis instead of the now open software. We do have the advanced methodology development on this area, like the causal inference and of the image study. So this whole picture hopefully can give you some bring back home message about the complexity of the big data analysis and the importance of the analysis technique in public health application, and also how to interpret and make this all results applicable in public health. And we will wrap up here, and we still have 5 to 7 minutes, and we will stop this session at 3:15 sharp. And please let us know if you have any questions, so we still have the few time to chat with the speaker. So I actually have very general question to the Dr. To Erica, Dr. Pong, and also Dr. Lee about, so both of you are doing the validation. And so first of all, the Dr. Pong, I just want to know, so for the whole training process, actually, you will have the validation procedure there. And how do you differentiate that from the silent evaluation in your whole data prediction model evaluation procedure? And on your flow chart, so if something happens, something bad at the silent testing procedures? So what will your strategy will be?
I'll answer your first question first and then ask for clarification regarding the second. So I think what sets our approach apart in a little bit is that we, in the silent evaluation period, we are looking at traditional model performance measures. But in the clinical effectiveness evaluation, the emphasis is on clinical outcomes. So if we can measure the impact on readmissions, we certainly will, but in other cases, we would look at other metrics of adoption. We would look at process measures if we don't have clinical measures, so that we can at least look at some proxy measures. We want to convince ourselves that this model is actually making a difference compared to current state. Because we know that these models don't maintain themselves over time and overall would represent a burden to our clinicians. And so we want to convince ourselves that the ongoing investment in these models are worth it. I mean, that is in some ways the bottom line question that we ask. So Jaja, can you clarify your second question? If something goes wrong in the silent evaluation phase, what do we do?
Yeah. What will be the strategy? Because I saw your flow chart actually after the silent evaluation, you will go that to the next step. So I just want to see.
Well, if it goes wrong, if something goes wrong and it can't be fixed, then we stop the project. Okay. But more typically, people try to fix it. If it's a technical issue that can be fixed, obviously they will fix it right there and then. If it's but it won't be the first time. We would have noticed during the silent evaluation when they start typical scenario, we've seen more than once, they connect, they proceed with the silent evaluation, they connect the predictive models to real-time data, and they realize that the data they had used retrospectively to build the models isn't available in real time because that's not part of the workflow. So for example, there was a surgical model that relies on diagnosis codes to drive a lot of the prediction, seems reasonable. But then at the point of the prediction, which is before the procedure, a lot of times we found out that the diagnosis code or the procedure code is not reliably entered into the system, because did you know that surgeons, when you go in for a knee replacement, they will actually ask for approval for 3 different procedures, and because they don't know which procedure they're really going to do until they go into your knee, but they ask for approval from the insurance company. So the diagnosis code at the time when the prediction needs to influence behavior may not be the actual procedure that you get. So these are some of the subtle things that happen in real life that may not be apparent when you're just looking at the data set.
Okay. Yes, thank you. So we do have another question from the Dr. Olitosi, but I think so we will talk that after the session, since we only have 2 minutes. I don't think that it's easy address question also. So let us wrap the session. And so thank you all for attending today's session. And please join us for the next at 3:30. We do have another EHR session, and which is has 5 speakers also. So please join us at 3:30 for the EHR session too. And you will have more chances to learn more story about the EHR application in public health. And also tomorrow at 12 o'clock, and EHR also help to organize the keynote speaker session on the flexibility and interpretability of the high-dimensional health data set. So you probably can know more about the EHR, the analysis skill at that session also. So thank you very much for joining this session. And so we will start the session here. Thank you.